Okay, good evening everyone. Welcome to our evening presentation and our AGM. If we've got more people coming in, good. So just before we start with the presentations, I just need to give you a couple of housekeeping notes. So please can I ask you to take a moment to check that your mobile phones and any other technical devices are turned off. And can I also remind you not to leave bags or personal items unattended at any time. In the event of a fire, the alarm will go off and we will leave this meeting by the emergency exit, so that's at the front and at the back. And we'll make our way to Storey's Gate exit. In the event of any other emergency, we'll be informed by a member of staff who will provide further instructions. So thank you for that one. So we're just going to start off with the AGM and presentations from myself and Nick about what we've done this year and what's coming up in the next year. Before we move on to our evening lecture. So, just a recap from me at the end of my year as chair as to what we've done and achieved this year. So, it's been a busy year. We've continued with our usual schedule of events as well as trying to add in some new ones and start up some new initiatives. So, on the professional development side, we've had 5 lectures here at the ICE. All very well attended and we've had good feedback. If at any point in the next year you've got any ideas for presentations or thoughts, then let Nick know and we like to take your considerations on board. We also held a lecture a few weeks ago at Warwick University, so we had a lot of the MSc students and other people located in the Midlands come and attend that event. And we held 4 workshops here at the ICE as well. And then in terms of site visits, we had 2 towards the end of last year, which was to the Northern Line extension, and we had the Tideway boat tour, so those were run as part of the National Tunnelling Day last year. We also held our conference in March 2017, and it was popular as ever. We had close to 100 people attending, about 15 presentations by young engineers and professionals in the industry. We will be holding a conference again next year, and we're very keen to continue that run of giving young people within the industry the opportunity to talk about their projects and the work that they're doing with the like-minded group of people. Schools and universities, so one of our other subgroups, it's been a very busy year for them. We've completed the teachers pack and trialled it at 2 schools, so we did 2 lots of 12-week courses at the Oasis South Bank Academy. So we ran our teachers pack, which is 5 lessons, as well as organising visits to the ICE and out to site visits as well. So that went down really well, and as a result, the pack's going to be available from next week on the BTS website, open to download from anyone that's interested. And the ICE are also currently developing their website, and there's going to be a new link to our teachers pack along with other resources that you can use for going out to schools and universities. We also ran a TBM naming competition at the same school as part of National Tunnelling Day last year. So that was part of a UKPN project in London, and the class also got to go out and see the TBM before it was launched. We attended 2 Big Bang fairs in the Midlands, so in Coventry, as well as in London. I think we had between 5 and 10 volunteers at each of those, so I think that's always a great event for us to go to, and we always need more volunteers to go to those events. So you'll see that coming out in the emails that you get requesting for volunteers. So if you are interested in that kind of thing, talking about your role and your experience, doing some activities with the kids for the day, then please do get in contact with us. We are always looking for people to do that. We've been partnering with the Postal Museum and helping them with their challenge days that they've had recently. They've got some good resources there, and we're kind of sharing the knowledge and experience and helping them with that. Next week, we're part of the I Can Engineer Awards Day with the ICE and the London Graduate and Students Group. So that's being held here in the exhibition space whilst they still have the tunnelling exhibition. So we're going to be doing a load of activities there with the schools that are coming in, and also promoting our teachers pack to the teachers and the adults that are coming along. And finally, we're also working with High Speed 2 and Tideway looking at collaborating with them and using our teachers pack and looking at what resources we can share on that side of things. We've continued to try and promote tunnelling, both within people that are in the industry, so all of us, as well as those outside. So we're up to over 20,000 Twitter followers and 500 Facebook likes just recently. So that's great. We've revamped our newsletter, which is now called The Dirt, so hopefully you've seen that come out. It comes out about every 3 or 4 months with a bit of an update on what's going on and upcoming events. National Tunnelling last year was a big success. We had a reach of about 2.5 million people online. So lots of different people and companies and people just in the general public who are outside the industry posting their photos and thoughts on there. So that was really good. We're running the same initiative and day this year. So it's on the 7th of December. So it's 5 weeks today. So we'll be running the same online campaign under Tunnel Day UK, as well as we've set up a new initiative which we're calling Target 1000. So keep an eye out for this because you'll see a lot about it in the next few weeks. But basically our plan is that between the 1st and the 7th of December, so the week running up to National Tunnelling Day, is that we try as an industry to get face-to-face contact with 1,000 young people. So tell them about our industry, tell them about the young members and what we offer, and just make them aware of the opportunities that are available. So if you already have an event in that time period, we will have presentations available to download online that you can take along and talk a bit about the BTSYM. And then we want people to tweet or on social media with the hashtag Target 1000, tell us how many people you've spoken to, what your event was, and basically we'll be having a rolling target throughout the week. So hopefully you'll all be keen to get involved in that as well. And then, of course, we've had our socials and networking sessions, as we always do, and that's one of the big parts of the BTSYM, and I think one of the most important parts, really. Find out about what's going on in other people's companies, projects, and we have had some good events at the same time. So we've been to the Flight Club, we had the pub quiz a couple of weeks ago, and then our Christmas social, as we have with the National Tunnelling Day. So, yep, this is the end of my year. So thank you all for being part of BTSYM and supporting our events and getting involved. It's been a great year being chair, and committee has been excellent and very supportive, and I wish all the best to our incoming committee. So now just to introduce Nick Bacrossan, who is going to be taking over as chair for 2017-2018, and I'll let him introduce the committee for the next year.
There we go. Thank you very much. I just want to say, so I'm working as the media committee chair last year, and don't think it's apparent just how hard Emma works behind the scenes every year. So I think she's going to be an incredibly tough act to follow. And if I can accomplish half as much as she did last year, it's going to be a successful year for me. So I'm going to take you through the plan for 2017-2018. So this is the build-up of the committee. So at the core is the BTSYM Committee, which includes the secretary, the sub-chairs, and our new role of the regional coordinator. Supporting them will be the associate members, and then we have the subgroup committee members as well. So our new secretary for the year is Graham Cooper from Atkins, and the new role of Midland coordinator is Harry Brunton. So this role is going to take what we do here with the BTSYM and try and decentralise it a little bit and identify opportunities up in the Midlands for us to get involved. Underpinning this, we've got a group of 8 young engineers who are going to be associate members for the year, but they're also going to be playing a key role in organising the committee as well, the conference. So taking over carrying on from last year, Sam Huckle from Balfour Beatty is going to look after the Professional Development Committee. Sam's got loads of great ideas, and I'm really kind of happy to see that he's back, and he's going to continue implementing them. Supporting him are Tom Doherty, Nicholas Dio, Carol Skavidis, Tom McGowan, and Richard Dollarhead. In media, Hara Kalajaraki from Dr. Showers is going to be taking over as media chair this year. Supporting her are going to be Alex Backhouse, Liam Greeny, apologies if I'm going to mess this one up, Wojciech Markowski, and Fautini Naichi. In Schools and University, Rashik Banderi from LBA is going to be taking over as chair for the year. Supporting him will be David Ashworth, Michael Lawless, Zachary Mahmood, Chris Moxham, and Chrysothemis Paraskevopoulou. I'm so sorry. So I've got, apart from developing the events that we carry on each year, I've got 3 goals that I'm keen to implement this year. One of them is decentralising our events and improving accessibility. So as a group for entry-level professionals in the tunnel industry, I want to improve our reach. So I want to host at least 4 events outside of London. So there can be lectures, workshops, site visits and socials. And also want to increase the materials available on our social media channels, such as YouTube. In terms of a second goal, driving sustainability, I think we need to drive this a little bit more, perhaps but through engaging a professional development committee, and also want to appoint a BTSYM sustainability representative who will be engaging with the main BTS committee on this. And then the third one is just improving engagement. We know that the industry is going through a little bit of a lull. So we need to make sure that we keep engagement going with the industry. So I want to make our lecture content more accessible for entry-level professionals and also covering broader topics. And I also want to implement a new system where we have company champions who are able to disseminate information within the companies and appoint BTS senior sponsors as well, who will identify people within their own teams that are able to come along. Just an update as well, we've got a few new social media streams, so please add us on Instagram. We've got a very exciting first story that went up today. And we've also got a new YouTube channel which is going to be populated with information such as our lectures that are being recorded. So I'm going to pass on to Emma, who's going to do our last introduction as outgoing chair for the lecture this evening.
Okay, so tonight we have Chrysothemis Paraskevopoulou. I think that's better up close. Is a tunnel and mining engineer with postgraduate studies on the design and construction of underground works. In September 2016, she completed her doctorate PhD studies under Dr. Mark Diedrich's supervision at Queen's University in Canada. Her research work is associated with the time-dependent behaviour of rock materials and the implications associated with tunnelling. In April 2014, she started working in a joint research project between Queen's University and ETH, that's the Swiss Federal Institute of Technology, on time-dependent laboratory testing. In February 2017, she was appointed lecturer assistant professor to teach MSc level courses on applied rock mechanics and engineering at the University of Leeds. So thank you very much.
Thank you. It's a great pleasure to be here. So today I will be presenting a lecture about rock engineering and underground space, investigating the effect of time in the surrounding ground. And I hope with this lecture I will raise your awareness of time-dependent behavior in tunneling. So when I give lectures and trying to introduce the underground space, I really like using this sketch. It is a sketch by an architect, Corbett, in 1925, and he drew how the New York City would look like in the 50s. And you can see he's not that wrong if you can see the underground world and the above ground world. So underground space is used by human beings from the early years, and we are talking about almost 3.2 million years ago, where the human beings used caves for their shelters. This is another example of different usages of underground space worldwide in Earth, and you can see that this tunnel was used for water course, and it's the Eupalinos tunnel that was recently declared from the ITA as the International Tunnel Landmark, and it is one of the first reported tunnels in history, in human history. Also, people used, even from 500 BC, underground space for creating rooms and spaces for water supply and storage. So here are examples how we use underground space today. And we use it a little bit in housing for offices to store files or other things in underground space. And this is why these days the sky is the limit and we cannot build skyscrapers for ever. And also we use underground space for industry and public infrastructures, public transportation and infrastructure works. And here is why we do that and why we should use the underground space. We should use it. It should be used actually and preferred to host needs or activities and facilities that are impossible or environmentally constrained or more expensive to be located on the Earth's surface. And we do that for two reasons. Underground space provides us stable environment conditions, temperature and humidity, as most of you may know. And it's a safer space from natural hazards, for example, earthquakes. But more specifically, why should we go underground? Because we can use the surfaces in different ways. And this is an example of the Museum du Louvre in Paris, where most of the museum is underground. Environmental restrictions. Here's an example before and after. This is a car park in Marseille, again in France. And this is how it looks today. It all went underground. Another example of this, you can see in Boston if you have visited. Here is a park, but before the park, it used to be a highway. Also, we have landscape and topography restrictions. This is the Gothard Mountain and the base tunnel that was constructed and opened recently in 2016, and also for social benefits. We use underground space, we build tunnels for water supply, for public parks, for limiting traffic conjunctions, subways and metros, etc. So, but in our industry, we keep pushing the limits. So I'll have here some examples of the longest different types of tunnels. So the longest railway, as you may know, right now it's the Gothard Base Tunnel, 50 kilometers. It was constructed in Switzerland, opened in 2016. Here is the Gothard Mountain. And soon, Austria would like to construct the longest tunnel, which is going to be 64 kilometers, and it's going to be completed in 2025. And here is the tunnel inside and the support system they're using right now. And the longest road tunnel is the, if I'm not correct how we can pronounce it, Lardendal Tunnel in Norway. It is almost 25 kilometers. What it is important to say here is because the driver cannot keep his attention for more than, I don't know, half an hour or 20 minutes where you have to drive in there. They have different color lights to keep the attention of the driver. The longest water supply tunnel is in the USA. It is in New York. It's almost 137 kilometers, and it was constructed in 1945. And because there is a leakage on this tunnel observed, now they're making a bypass. And the longest underwater or undersea tunnel is the famous Seikan Tunnel in Japan, and it connects the mainland of Japan with this island, Hokkaido, excuse my accent, and pronunciation. And here are some pictures of the tunnel. And finally, Norway reported that is going to build the biggest, but not the longest, ship tunnel, the Stad ship tunnel, and it will be completed by 2023. And here are some pictures of how they have imagined it. But in the UK, as you may know, there are lots of canal tunnels, and the longest one, just for your information, it is located near between Sheffield and Leeds here. It is called Stand Edge, and the length is almost 5 kilometers. And the deepest point within the tunnel is 194 meters. It was constructed and opened in 1811, but it was misused and abandoned by the 1940s, and now it's reopened since 2011. So if you have the chance, it would be nice to visit it. So the question here is, how do we get here in this stage, in this final stage of oral project, underground projects, from these situations where you can see failures in tunnels due to time-dependent effects. For the short-term rock mass behavior and for the design of our tunnels at the initial stages, I think we are doing pretty well, right? We use failure criteria, just have put here indicative a few tools that we use. Some of us, or you use the rock mass classification systems. But what does it happen when we want to predict the long-term behavior? And this is important. One of the most important applications of the long-term behavior is the design and construction of radioactive nuclear waste disposals. And here are a few examples or designs from different countries. You can see all of these countries: Switzerland, Belgium, Germany, France, Japan, Canada, Spain, the States, and recently England as well, are trying to build those underground spaces for nuclear waste disposal. So time effects in rocks. I like using these pictures in my presentations because what I find remarkable on this is like these marble benches keep standing without failing after so many years. Again, in the Efpalinus tunnel, it keeps standing, no support, after so many years. Other examples of this time-dependent deformation, you can observe the deformation on pillars on salt mines, or here, this is the famous San Martin-Laporte tunnel, or time can deteriorate the rock mass behavior and lead to sudden failure, rock burst mainly. So I will try to give you an introduction and a few information on time-dependent phenomena. I hope to not to get you too much tired. So the time-dependent phenomena can be either due to a change on the state, stress, strain, or a change of the property, Young modulus, friction, Poisson's ratio, etc. And according to its reversibility, can be either elastic, inelastic, or irreversible. The physical response can lead to creep, contraction, dilation, relaxation, or degradation. And the physical mechanism can be due to solid rheology, damage, discontinuum elements, physical-chemical changes, while the rate can be controlled by the chemistry, the fluid mobility, the stress deviator, the temperature, the pressure and humidity, as well as the confinement. Then we could have creep, which is the time-dependent deformation of rocks and rock masses subjected to constant stress that is less than its short-term strength. It can lead to consolidation or dilation, which is the time-dependent volume change of shrinkage or creation of pores. Swelling, which is the time-dependent volume increase caused by the absorption of water in the zone close to excavation. Stress relaxation, which is time-dependent stress decrease where at least one of the strains is constrained or confined and remains constant. and strength degradation, which is the time-dependent strength loss that is usually chemical assisted and driven by stress corrosion. In tunneling, we usually or often deal with squeezing, which is the time-dependent large inward closure of tunnels that can lead to complete shear failure, buckling failure, or shearing and sliding failure. But we can still have swelling or strength degradation, stress relaxation. What is important here to say is that all of these phenomena and mechanisms can act either simultaneously or individually. So the observed overall tunnel wall displacement can be a function of all of these and a result of all of these different phenomena. Depending on the confining pressure and the temperature that a material has been formed, can be either behave as brittle or ductile. And this is important when we're dealing with time dependency, because a potasse with time can keep deforming. However, a more brittle, for example, limestone, will fail in a sudden manner. And I will just base my my discussion here on creep behavior, and I will say that regardless the micro scale mechanisms of creep, that can be either dissolution creep, dislocation creep, diffusion creep, pressure solution, like all of these words that most of you have heard but you have forgotten, can lead to creep behavior, which is typically described with this curve, and it is defined by 3 stages. Not always all of these 3 stages are distinct though. So at the beginning we have the elastic response, and then as the load or the stress is kept constant, we have increased deformation or displacement or strains here. So we have the primary stage of creep, and then the rate of the deformation changes and becomes constant. We have the secondary stage of creep, and then at some point we have the accelerating and tertiary creep where failure might occur. So all of these time-dependent phenomena can be simulated with time-dependent models. So usually we use empirical formulations, but which are basically formulations based on experimental data, of curve fitting data, general theories that are mainly based on the overstress theory of Bertinas, and other researchers have expanded and extended this theory. For example, De Bernardi has created another constitutive model to describe this time-dependent behavior of specific rock masses. And we have rheological models, and I will focus on those. Some of you who might do modeling for on your job, you might have seen those things. You might have tried to neglect them, but I will just give you an overview to understand how these things work. So rheological models are basically mechanical analogs that consist of springs to simulate elastic behavior, daspots to simulate this time dependency, viscous behavior, flow. Keep in your minds that dashpot means flow, either slow or fast flow, and sliders we use for plastic behavior. So if we arrange these mechanical analogs in different ways, we can simulate different behaviors. So I'm going to focus on viscous models, and I will give you a brief overview of the viscoelastic that we use for time dependency and mainly in creep. So if we put the spring and the Maxwell together in a series, we have the Maxwell, we have this part of the curve, the secondary stage. If we put it in parallel, we have the primary stage of creep. the Kelvin model. And if we put those two Kelvin and Maxwell in series, we have the Berger's model that can only simulate the primary and secondary states of creep. When we talk about viscoplastic models, we always need the slider. Remember, plastic is a slider. So again, with different arrangements, we can simulate different behaviors. And I will focus on this model that I will be using later in a numerical analysis. I will just briefly giving you a description. And so we have the CVisc model, which is actually a viscoelastic plastic model. And it is a Berger's model, as you may see, with a slider in series to simulate the plastic behavior at the end. And in order to use all these models, we need parameters. And how do we get parameters? From laboratory testing. So from a UCS baseline testing, and this is a typical stress-strain curve, we get design parameters. So I'll just go through with that very quickly. At the beginning, when we load the sample, we have the crack closure, the pre-existing cracks closing. As we increase the load, we have the linear elastic behavior until the first crack initiates. And we have this CI threshold, crack initiation threshold. As we increase the load further, more cracks start to grow and propagate. And as they interact with one another, they have a stable crack propagation until the crack damage threshold, where after this, we have the unstable crack propagation that can lead our sample to failure. But this is how we can get time-dependent parameters, by changing our boundary conditions. And remember that we need to have a load or a stress that is less than its stress and than the short-term strength. So we should be on this part of the graph, not closer to the UCS. And we can have relaxation tests or static load tests. So by either keeping the stress constant, we have creep test, or the deformation constant, we have the relaxation test. And here it's just a description of those two tests. So loading until a desirable stress level lower than the short-term strength, and holding the deformation or the strain constant. Then we can observe the stress, how the stress relaxes. And this is something that we observe usually on tunnel faces as we excavate it, or like whenever we create an opening in the underground space, you get stress relaxation. So that's the idea behind it. And here we have the creep or the static load test. So we load the sample until a certain threshold, stress threshold, and then we keep the stress constant, and we see how the strains behave. So in a relaxation behavior, we do have 3 stages as well, and by fitting our experimental data to idealized an idealized relaxation behavior, you can get the viscoelastic parameters. And there, this is, I'm just showing you this, but because I want to state that there are tests, relaxation tests out there, and there are parameters. So if you dig a little bit in the literature, you can find this easily. Similar to creep, the only drawback with creep is that you need to have time to have a creep test, and a relaxation usually the duration of the test is faster than the creep test. For example, you can, in a brittle material like limestone, you can have a relaxation test within 1 to 2 days. A creep test can last even a year. So That's something else to keep in mind. So here, just one of the results I was doing in my PhD. I was curve fitting. This is real data from a creep test on limestone, and I was curve fitting and finding these parameters. Something else to keep in mind: creep tests, okay, they might last longer, but they're good when we're dealing with strength degradation and how the strength decays over time. That can give us an indication of the long-term strength of the rock. So again, this is another data set I put together with many different rock types on long-term strength. So, for example, we have two different rock types, limestone and granite, and even though granite is usually stronger if it is not weathered than limestone, in the long run, the limestone is stronger than the granite, as you can see here. Think of it as a stress, it's normalized stress, and time to failure. And because of the heterogeneity of the granite and the different mineralogy and the different rates that the minerals flow in granite, they can make the granite fail and not be able to sustain as much strength as the limestone, which is more homogeneous. So I'm just trying to trigger your mind and when you're dealing with different rock types. So this is an overview of the long-term strength. We have the driving stress ratio here, time. All these dots, the filled ones, are samples that they have failed. The open circles and shapes are samples that they haven't failed yet. So when we're dealing with brittle materials, we expect failure to occur within an hour when we load it in this threshold above crack damage threshold, when we have this unstable crack growth, if you remember, and below CI, where the crack elastic region and crack initiation, we are not expecting damage. All of these points, you should think of them as moving points because they're going to fail, but later on time. So again, just an overview of these two type of time-dependent phenomenon, creep and relaxation. They both have they can be described by 3 stages, and similar responses can happen depending on the load on the rocks as the load and the stresses changes over time. So, okay, we have figured out a way to find our parameters. Now, what we do with these parameters? I'm going to just give you an example of a numerical analysis I did using this time-dependent behavior in a tunneling environment. Before I do that, I would like to say a few words about convergence and convergent confinement method and characteristic lines, and how using this method, how we would approach a time-dependent behavior in a tunneling environment. So the convergence is usually the inward, or it can be defined as the inward tunnel wall displacement, and this can be a function both of the tunnel advancement, right, here, and the time-dependent behavior. So function of both the location of our phase and time. And we use this approach also with the ground reaction curve, which shows actually the decrease of the internal pressure PI. Most of you might have seen this before. So if we assume that this is a tunnel and this is our phase, our internal pressure in front of the phase equals the stress, the in situ stresses, correct? And then as we progress in the tunnel, this PI starts to decrease. until we are very far away from the phase where all our displacements have stabilized and reached the maximum value, and this PI is 0. So we use this PI usually to calculate our support and when we should put our support in our tunnels, our temporary support. And usually it's a it is a linear curve, it is a line, but depending on the behavior, if the material behaves elastically, and depending on the behavior, on the behavior of material, it deviates from this linearity. So this is elastoplastic behavior, for example. And I'm not, okay. Another tool we're using for the longitudinal, on this convergent confinement method is the longitudinal displacement profile, this LDP, and you can see it here, along with the characteristic line as well. And it actually tells us how much deformation has occurred as a percentage of our maximum anticipated deformation, tunnel wall deformation. So we should know that by now, that when we are actually at the tunnel phase, almost 20 to 30% of the total displacement or deformation has already taken place, and 70% of that will occur with time as our tunnel phase is progressed. And there are many formulations and analytical solutions of these LDPs, or how to calculate LDPs depending on the material behavior, if it's elastic or elastoplastic. But they neglect to encounter time. So if you don't encounter time, you might end up with these unfortunate situations. This is from the Yakambu tunnel, and you can see the remaining parts of the TBM. It had to be abandoned. So in this case, they underestimate the total displacement. So they got their TBM trapped. There are, however, analytical solutions for these time-dependent models that I was explaining to you before in a tunneling environment, in referring to circular tunnels, the simplest geometry. And however, they don't encounter the tunnel advancement. So either you have one or the other. And I will be focusing on the Kelvin void, the primary stage of creep, where after a while, the displacement or the strains stabilize, reach an asymptote. And I put this figure so I can put all this information together, but maybe let's take a step backwards. So imagine that this is our tunnel, and our material, our rock mass around it, is elastic. As we know, it will reach the maximum tunnel wall displacement after 2, 3, 5 diameters away from the face, depending on the material, right? But if this is not the case, what if we have time-dependent behavior or potential? So these, even primary stage, this maybe it needs more time for our total displacement to take place. So this means we need more diameters away from the face. Maybe we need 5, more than 5, 8. But what if they don't stabilize? What if the rate changes? And then we have the secondary stage of creep here. Then we have the Maxwell component in our model, right? And if they keep going, we are okay. But if they keep going with a constant rate, we have the secondary stage of creep. But if there is one of these at its critical time, there is another accelerating stage where failure will occur. Then all of this medium would behave as elasto-viscoelastic plastic. But in our analysis that I will be showing to you, I have neglected this tertiary stage of creep. I am only showing you the elasto-viscoelastic medium. So no failure. Just keep going. And imagine this, like a tunnel that will keep deforming until closure takes place. So I will just give you an example of a numerical analysis, parametric analysis I did with FLAG, Itasca software. I analyzed two cases, drill and blast. You can see here the jumbo and the TBM. And the only difference between those two are the excavation, it's the length of the tunnel advancement. So my only separation was between those two methods was the tunnel advancement. Drill and blast, 3 meters, usually, and 1 meter for TBM. And I create this material, this rock mass, as a viscoelastic material. I increased the cohesion and the tension, so it become elastic. And I use that CVisc model I showed you before. And I analyzed two sets of parameters, two different sets of viscoelastic parameters. The main difference was this set of parameters to have a difference of an order of magnitude in this parameter, which is called the retardation time. And I will show you through the results what this thing does. But before I started my analysis, I wanted to compare my analytical solutions with numerical results. So I used the elastic and the hopeless and Dietrich elastic. I made it elastic. And the Kelvin void numerically, and the Kelvin void of Panet's equation. And the results are pretty good. So here is displacement, and this is distance from the face. And all of these views are closer views of these rectangulars. You will see many figures like that from now on. They're called, these are the LDPs we were talking about before. So for a drill and blast case, up we have one set of parameters, down we have the other set of parameters. Again, closer views, and all of our results are normalized now, so we will have a reference. What we can see, and these. So my boundaries are the elastic limit and the Kelvin void. And this is an LDP assuming that I excavate the tunnel at once, and then I let the creep do its own thing. I didn't take into consideration this tunnel advancement, like how much I progress every 3 or 1 meter. The colorful lines here have encountered the duration of this tunnel advancement. So and they refer to numbers 2 to 8, and they refer to hours. So this is if my tunnel, like the whole tunnel excavation support, and again this tunnel cycle the duration was 2 hours, 4 hours, 6 hours, 8 hours. Okay, so. The two set of parameters with this retardation parameter, one order of difference, it can be seen here. So what does this tell us is that the higher the retardation time, or these parameters that this ratio, it converges sooner to our total deformation or displacement, tunnel wall displacement, than the other set of parameters. So depending on the viscoelastic parameters that we estimated in the lab, and all of these things that I was discussing previously. And again, for the TBM, you can see the difference between the tunnel lengths. From the TBM, On the TBM analysis, you can see that it converges closer to the tunnel face because the tunnel advancement is one length. So one length, 8 hours, 1 meter, 8 hours, 1 meter, 8 hours. So at the end, you will get your maximum tunnel wall displacement closer to the face, but in a longer period of time, if you understand my thinking. And on another set of models, I encountered the secondary stage of creep as well. So the tunnel will keep deforming until total closure takes place. So drill and blast, and again, TBM. The question, however, was in my models, when does creep start? And you can see it on both cases, drill and blast and TBM. It starts after one diameter after the face in the open space, in the excavated space. You can see that the elastic with the gray line, LDP, deviate, or the time-dependent ones, the viscous ones, deviate from elasticity after this distance. So this is normalized, but it is one excavation after the face. And again, I have here put the analytical solutions and the numerical results. Analytical solutions are with the dashed lines. Numerical results are with continuous lines. And what I want to show here is that you cannot have both. You can have both in numerical modeling, but you cannot use analytical solutions in order to capture both the effect of both the tunnel advancement and the time-dependent behavior when you're designing. So right now, I'm working on back analyzing this with tunnel data, real tunnel data, to produce semi-analytical closed-form solutions you can use for both, that encounter both effects, and analyzing supported cases. So I hope I didn't bore you with all of this, but I would like to leave you with these three conclusions. They're focusing on the analysis. The utilization of conventional methods used to predict the longitudinal displacement profile of the radial displacement have limited application and fail to capture the overall displacement over time. The excavation method also controls the overall displacement. Different results may assist the selection of utilizing drill and blast over TBM excavation if it is proven financially affordable. Being able to predict and estimate the rock mass response due to one excavation method versus another can lead to project optimization. And optimization of the design usually involves the appropriate selection of the excavation method and support system that would allow the rock mass to further deform over time, avoiding overstressing that could otherwise lead to support yielding and abrupt rock mass instability, safety use, and of course cost overruns and project delivery delays. And it is encouraged to further examine the geological model, the geological behavior, potential, and utilizing all data and information available that will improve the design of the overall project. And I will leave you with this, another visionary, entrepreneur. I found this image online a few days ago, and this is how they're thinking the future of underground space will be. So with this, I would like to thank you. And if you have any questions, please do not hesitate.
Okay, thank you very much. Does anybody have any questions? Anyone? There we go, one in the middle.
Thank you. What is the effect on the long-term behaviour of soil around the tunnel? Once the tunnel's been built, say it's in a region that gets a lot of earthquakes, what kind of effect does that have on creep and the kind of behaviour you were talking about?
You mean on your main support?
Yeah, on the behaviour of the soil in the long term.
It will keep deforming, and it will build up your support load on your main support. So we should, like, there are reported failures worldwide on this. And even, like, if you can project or estimate how much you're anticipating, you can reduce your tunnel cost, overall tunnel cost on support. Or, like, you don't have to deal with this unfortunate situation I was showing you before.
Thanks.
One just on the front here.
Thank you very much, Chrysothemis, for this interesting presentation. It's been a while since I worked on these things, but I hope I remember something. I would like two things to ask you. First of all is with regards to the laboratory tests, and in order to extract the parameters for the design. If the rock mass is quite homogeneous, you have, for example, an intact, let's say, granite or limestone, or you have a very hard marl, it's easy in a way to simulate your laboratory sample and try to extrapolate the results for the overall rock mass. But what happens if the rock is quite blocky, too blocky, and how, in a way, you can extrapolate the results from the laboratory tests to be representative for the overall rock mass or the surrounding material?
You mean to encounter the scale effect in heterogeneity?
Correct, yes.
This is something that we are researching, so I don't have like an answer. It's up to critical judgment of the engineer on how to approach this, but a sampling of different rock mass types on these or classes, that would be good. And also trying to quantify the uncertainty on the parameters on your design overall, that would be a way to go, I think.
And one more thing, if I may. Usually, if this is what, in a way, we did in the past, if you want to simplify your design and take into account the time-dependent effect, what we used to do is we used to reduce by a percentage, 20, 30, 40%, the modulus of elasticity in our design, especially in numerical modeling, and that would be, in a way, the long-term modulus of elasticity, which would, in a way, increase the deformations. So by that indirect way, we take into consideration the time-dependent behavior of the rock mass. Do you think that this kind of approach is appropriate, and is there any range that we can, any percentage that we can reduce the initial intact modulus of elasticity in order to take this into account?
For simplicity, yes, and if, like when you have to manage your time and deliver your project, yes, this might be an easy way to go, just to be on the safe side. But I'm not sure if this approach always applies to the projects. Like if you're dealing with materials that they will flow over time, even like a little bit, then I'm not sure if that would give you the best or the accurate result. So I'm encouraging, I want you to encourage to spend more time and actually do testing to get real parameters to put into your design.
Thank you very much.
Any other questions? Oh, sorry.
Hi, first of all, great to see you again after the World Tunneling Congress. How are you dealing with the water? Because in the instances where you have big deformations like squeezing, it means that the deformability characteristics are low. Typically, you have clay-type material. You have undrained conditions. First of all, how do you deal with the water in the simulation?
In the analysis I showed, I haven't, to be honest. So I'm only considering time, no pore pressure change or hydro-mechanical behavior. Mm-hmm. That's like, will make your model more complex, which is going to be computationally expensive. So yes, in an ideal world, you can always simulate or try to simulate the real problem into your model. But if you have all the time in the world, yes, you can do it. But I'm not sure how easy it is to do it in practice.
Also, considering you did drill and blast and you did TBM, I would imagine TBM, you either do it with segments if you have a closed phase, or you do it with, with open phase TBM. If you have segments, you block the water. You have water pressure in the segments. The behavior is different. You have drill and blast, you probably have drainage channels, so, shotcrete layers, again, different behavior. So that would be quite interesting to understand how water is involved in the whole scenario of analyzing and simulating. Thank you very much.
You're welcome. It was just a simplified model. Just wanted to show you the result.
One more question in the middle.
Congratulations for the presentation. My question is there any way, even hypothetical, not technically feasible today, hypothetical based on the physical behavior of the rock, to stop or reverse creep effects in rock?
Which effect?
Creep
effects. If you change the stress state, I think you could. But I'm not sure how realistically they could be.
If, for example, you drill an array in an existing tunnel, drill an array of boreholes around the tunnel to create more space, more gaps that they can relieve, for example, the stress outside the support.
You mean over-excavate and to allow the deformation to occur and...
No, there's something you do in the design, but as the creep develops in a constructed tunnel, can you, for example, drill an array of boreholes in the fashion of anchoring around the tunnel, but post-construction of the tunnel?
To get stress relief.
Yeah. For example, it's a first thought that comes to mind. But
I guess you could. Could or I have to think about it, but it might be. I'm not sure if people do it.
No, apparently
I don't think so. That's an interesting idea.
Any final questions? Go for it, Tom.
Yeah, thank you very much for a good presentation. I was wondering, as a designer, if you were to look at the long-term behavior and predict a tunnel to collapse or close, are there any specific things you have to think about in designing support other than putting in a stronger, stiffer liner sooner? Or
the time of installation is a key characteristic, I believe. So it's up to you, and it's the engineer's judgment when the support should be applied and how much deformation you have allowed the rock mass to deform.
so are there any particular kinds of support that you think would be best?
Obviously there is yielding support, if you have heard of it, or leaving open gaps in your support so they will close eventually. But then again, you have to know how much deformation you would be anticipating, right?
Okay, thank you very much, and thank you very much for your presentation, Chrysothemis. So one final thank you to her. And then just a final few slides from me. So just a reminder again about National Tunnelling Day in 5 weeks' time, and also our Target 1000 initiative. Please get involved. If you've got any ideas or need any support in arranging activities, then get in contact with any of the committee. Next one, please. So the next BTSYM workshop is on construction contracts on the 16th of November. So that's in the afternoon, just before the BTS presentation in the evening. So next. So this is that presentation on the same day. Finsbury Park Squareworks, so presenters to be confirmed, but I think that'll be a really interesting presentation. Next. And then the final BTS lecture of the year is on the Waterview Tunnel in New Zealand. So we've got speakers coming over from New Zealand, so I think that'll be a really interesting insight into what they're doing on the other side of the world. And I think that's it. So thanks very much for coming this evening. Hope you enjoyed the AGM and our presentation, and I hope you'll all join us in the bar downstairs for some food and drink this evening. Thank you.